Okay, I'm used to a lectern. Thank you very much, Luis. It's an enormous pleasure to be here. I remember a few years ago, more than 2 years ago, when Maisa, who was Maisa Nara dos Santos, whose voice you will hear, but who is not here, she's on a 2-year-long honeymoon, came to me and said, Michael, I was at Silver Laser and they asked me to help organize the next event. I said, no, don't do that. It's going to ruin your life. And so Luis did it instead. And I guess it ruined his life, but we're very, very grateful because we're all here thanks to him. So thank you very much, Luis. Okay, very good. Okay, so I have this lots of words in my title, and oops, thank you. Let's see if I turn off the projector. No, it really projects. Let's see if it goes forward and backwards. Good. I have this lots of words in my title, and those of you who are experienced know that when you don't know what you're going to talk about, you can put a lot of these, general things into your title and your abstract, and then you can decide later. So this is what I did. And what I'll really be focusing on is the work that we did with LiDAR to understand the changes in forest structure resulting from forest degradation in the Brazilian Amazon. And there were many people, this is only a partial list, that helped with this work. Several of them are here today, and the key person again was Maisa Nara dos Santos, who organized all of our data that we collected and made available to a large community. At the very end of the talk, I'll be talking about that data and how we got it and availability. So thank you all of these people who contributed. And I've done my little preview. I'll focus on degradation of Brazilian Amazon forests. An important emphasis of our little program, which was called Sustainable Landscapes, or Paisagens Sustentáveis in Portuguese, it was on carbon accounting. That's what paid the bills. And I'm not going to be talking about better ways to do carbon accounting, although a lot of you probably are doing just that and doing it better. This program was implemented by my home organization, the U.S. Forest Service, and EMBRAPA, which is Brazil's National Agricultural Research Service. And finally, we were supported by USAID and the U.S. Department of State, and that's the Department of Brilliant Names. Who could be against sustainable landscapes? In this age where in some countries, that shall not be named, climate change is a bad word, sustainable landscapes are still very, very nice. So this name is itself sustainable. Okay, so I'll be talking about what are degraded forests, how we can use LiDAR to study them, the causes, briefly, of forest degradation, spatial extent, which is not based on LiDAR data, at least not yet, estimation of carbon loss from degradation, and then some very, very rough regional extrapolation just to give you an idea about the importance of this process. Finally, at the end, I'd like to talk and reflect a little bit about the program that we had, and that is in a very low-key phase, still going, something that Luis asked me to do, and I'm a little bit embarrassed about, but I'll do it anyway. Okay, so what's a degraded forest? This is a mouthful. There are lots and lots of definitions of degraded forest. This is mine. A degraded forest is a forest where the rate of exogenous disturbance, that means disturbance coming from the outside, not sort of the natural cycle of forest, recruiting and dying, is greatly exceeded the long-term average rate of exogenous disturbance. So there is natural exogenous disturbance like wind, but this is something that comes from outside people generally and leads to effects that can be distinguished from old-growth forest structure and composition. So it's a change in the rate of disturbance. Where does that change come from? In the Brazilian Amazon, intact forest is degraded usually by two pathways, logging, fire, and also by deforestation. Deforestation leads to non-forest areas, regeneration into secondary forest. It also leads to the creation of edges and fragmentation that itself can lead to degradation processes. Inside the degraded forest, I need to back up. Doug was right. Inside the degraded forest, you have things going on like logging, fires, and these can recur, and log forests can burn. So, degradation and forest structure. We took airborne data, and these are photos of forests sideways, and these are sort of top-down canopy height models from intact forest, which is high, to very heavily degraded forest, with sideways profiles showing very even sort of Gaussian profiles for the undisturbed, with very skewed profiles for the heavily disturbed areas where you see, very low profiles. The hot colors are high here. We use these structural changes both to diagnose what's happening, to measure biomass, and also to classify the stages of degradation. So in the Brazilian Amazon, we collected data, this is up until 2016, from these areas, mostly in the area which is known as the arc of deforestation. We have intact log, burn, and forest data from all of these different areas. And this is a view of the Amazon, the red being areas that were deforested in 2000 to 2010, the gray being areas that were deforested before that, the green being mainly intact, although much of that green area is also logged and some of it is burned. We collected commercial data. We paid commercial operators here in Brazil, very professionally done, excellent job from our vendors who are unnamed. I'm not allowed to promote commercial operations. But we collected it with this instrumentation. We flew relatively low. We had a very narrow scan angle because we wanted to collect nadir data primarily. And we had a very large side lap. Minimum return density was 4 returns per meter squared, but generally it was far higher. And we required our core vendors to cover 99.5% of the area. So we have some very rich data sets with lots of points, at least for that time. Nothing compared to what you guys can collect today, I'm sure. And we developed calibrations for biomass. These are not sort of unusual. They use the usual sorts of metrics like mean height, and they have the usual sorts of problems of some very heavy plots, because the plots themselves that we use for calibration were a quarter hectare. A quarter hectare is fairly large, but in Amazon forest that may have 1 or 2 large trees that can skew your results. But in general, we have these findings that all of our sites, and regardless of degradation state, fall on the same calibration curve. And this was a great and wonderful surprise for us. We could go out and survey forests from the most degraded with biomass down here in, a few tons per hectare, back, forward, to forests that are, old growth with very high 300 kilograms of carbon, 300 tons of carbon per hectare, and use the same calibration. That was a nice surprise and makes our lives much easier rather than having to stratify our forests in order to use different calibration curves. So we went on from there, and we compared the data that we had from dozens of sites. We looked at the different distributions of biomass for different degrees of degradation, from intact and reduced impact log forest to heavily burned forest, and these were the distributions of biomass that we found. We compared the biomass to global maps. I just saw one example that was based on an interpretation of glass and MODIS primarily from Alessandro Boccini. We took our data and we subtracted Boccini's data, and what we found was at the low end, they would overestimate biomass. At the high end, they would underestimate biomass through their global map. And that's a fairly typical result when we compare that to other global estimates. the work that you do with these global extrapolations using models like random forest, which was used in this case, they tend to predict the mean, and they do tend to underestimate at the high end and overestimate at the low end. And we found that for the Saatchi data set, and we couldn't really compare to some of the other data sets because they started to use our data, so the comparisons would have been circular. So if you put your data out there, you do have that disadvantage. Okay, going on. So what is degradation? One source of degradation is selective logging. Selective logging, many of you are foresters know, is you take out a certain number of trees in an area that have high commercial value. This is the primary mode of logging in the Brazilian Amazon. Brazilian Amazon has relatively few commercially valuable species, partly because of the distances and the expense, partly because of the very high diversity. And so only 6-8 trees per hectare are taken out in rich stands close to markets, and in poor stands far from markets, that number can fall to 1 or 2 or 3. Log forest has big gaps. It has little trails. This is a very nice one. They don't always look that neat, and they don't always have this nice canopy cover. Forests have gaps and decks where logs are landed for transport. All these features are visible, certainly in LiDAR, and the features are visible in some cases in other remote sensing, like multispectral Landsat or Sentinel data. Back in the early 2000s, we did a study that, using Landsat, tried to catalog how much logging was out there. Greg Asner published this in 2005. Here's the arc of deforestation. Again, logging occurs in the arc of deforestation, and it ranged between 12,000 and 20,000 kilometers squared per year. That's a lot of area, and was an area that was comparable to the amount of Brazilian Amazon deforestation at that time. So logging covers a lot of area. Thanks to colleagues at EMBRAPA, Marcos de Oliveira, in particular, and colleagues from the Forest Service, Hans Anderson, we started to learn about logging using our data. This was before we came here, and this was using our first acquisition, actually. And what we learned was, well, we could calibrate biomass. That wasn't a surprise. We could measure it in log forest. We could see the logging roads and trails, and then we could see the canopies that were removed. And this is probably not surprising at all to any of you there, but it was really a lot of fun back in 2011 when we were subtracting off the 2012 data that we acquired from 2011 data from 2010 data. The reds were canopies that disappeared, and lo and behold, they follow these skid trails. So we could get down to the very essence of what was happening in terms of forest change using our LiDAR remote sensing. Again, I suppose this is just sort of old stuff to all of you, but at the time I thought it was quite fascinating. And we've gone on from there to look at the changes in LiDAR, changes in forest logging, and how durable those changes are. So Akena Pinage, who was a student who worked with our group, she classified canopy damage here. These are all in green gaps that are at least 10 meters squared in area and are no higher than 10 meters from the ground. As our gap definition, this here is a main road. These are all areas that were logged. They show different years of logging. And this is understory damage, which was measured using a relative density model. We took the number of LiDAR returns below a half a meter and compared it to the number of LiDAR returns in the entire column. And where we get bright responses, that's where the lower returns that aren't necessarily ground returns occupy a high proportion. So these are the areas of ground damage. And you see from these areas that were logged several years earlier, the ground damage is difficult to see. You see from the recently logged areas for images taken in 2012, the recently logged areas show up much more. So this ground damage tends to disappear into the regrowth that happens naturally in the forest, but the canopy damage takes a long time. In fact, it takes a decade, 2 decades, or 3 decades to recover. And that means that logging leaves a long-term visible imprint, one that we can measure for a long time, and also one that is very easy to quantify using logging data at this scale. LiDAR data at this scale. So this just gives another view of the same thing. This is the canopy damage. You can see that it's relatively constant over these years from 13 back to 8. These areas, years of logging, and we took this data in 2014. As we get somewhat older, those gaps are filling in. They mostly fill in from below. They don't fill in very much from the sides. The understory damage disappears much more quickly. Just a few years after logging, 3-4 years, that understory damage is indistinguishable from the background. And so we know that there's vigorous regrowth in the understory, and this turns out to be an excellent way to diagnose logging initially, immediately following the logging, but not over the long term, whereas the canopy damage is a great diagnostic for at least a decade.